Today's topic is fundamental matrix and linear system. Welcome to Ovi's Math e-Pathshala. Press the bell icon and subscribe my channel.
हाँ सर बिल्कुल
So in the previous class, uh, we have defined that a 2 cross 2 matrix phi whose columns are solutions of the system. That is, what was the definition of a fundamental matrix? That is a 2 cross 2 matrix phi whose columns are solutions of the system x dot equal to ax, and the solutions are linearly independent. At T0. Then this matrix is called a fundamental matrix of the system x dot equal to x at T naught. And I have also discussed one example regarding this matrix, and that was the example can be given as A is 1 0 minus 1 3, and we consider the system x dot equal to x. The solutions are x1t is column vector 2 1 e to the power t, and x2t is column vector 0 1 e to the power 3t. Now at t equal to 0, these two solutions are linearly independent. x1 and x2 are linearly independent. Why they are linearly independent? Because if we put t equal to 0 here and here, then the solutions are x1 is the column vector 2 1 and x2 is the column vector 0 1. Then we can evaluate the determinant 2 1 0 1, and the determinant will be 2. So 2 is not equal to 0, and therefore x1 and x2 are linearly independent. And for this reason, we can conclude that the matrix phi equals to 2 e to the power t0 e to the power t e to the power 3t is a fundamental matrix. At t equal to 0. One can also check that the matrix phi dashed, which is given by 2 e to the power t0 e to the power t plus e to the power 3t 4 e to the power 3t. This is also a fundamental matrix at t equal to 0 for the given system, because again this satisfies for the given system. X dot equal to Ax. Yeah. This shows that the fundamental matrices for this system are not unique. And we can also have in general that fundamental matrices actually are not unique for a given system. Not for this particular one, it is general. That is, fundamental matrices are not unique for a given system. And note that every system x dot equal to x has a fundamental matrix, and this is very important, that every system, given any system x dot equal to x, this will have a fundamental matrix at some t0, which will be evident from our next theorem. The definition of fundamental matrices will give a necessary and sufficient condition on a matrix to be a fundamental matrix, which is as follows. So suppose you are just give a matrix is given, a 2 cross 2 matrix phi is given. When shall we say that this matrix is a fundamental matrix of some system x dot equal to Ax at t0? What is the necessary and sufficient condition which can be imposed on the matrix phi to make it a fundamental matrix of a system x dot equal to Ax at some t0? So this is the next theorem. So the statement is a 2 cross 2 matrix phi is a fundamental matrix of a system x dot equal to Ax at some t0 if and only if. What are the conditions? Number one is phi is also a solution of the system x dot equal to X. That is, if we place phi instead of x in the place of x, then we will see that phi dot equal to a phi. That is, phi is a solution of x dot equal to X, that system. And the second one is determinant of phi at t0, it will be not equal to 0. And this portion is needed because we are to satisfy the conditions of a matrix to be a fundamental matrix. And the definition of fundamental matrix is that at t0 the columns of the matrix 2 cross 2 matrix 5 must be linearly independent. And when do we call that the columns of the matrix phi, these are linearly independent? If and only if their determinant is non-zero. So this condition is needed. So let us have a look on the proof. So suppose if we let phi be a fundamental matrix, of the system x dot equal to ax at some point t0. Say phi is the matrix consists of two column vectors, one is x1t and another one is x2t. Yeah, where by the definition of a fundamental matrix, these two column vectors are actually solutions of the system, solutions of x dot equal to x. And not only that, they are linearly independent at t0. At t0. And therefore, what is phi dot x? So we apply derivative to the function phi t, to the matrix phi t. So phi dot t is x1 dot t, x2 dot t. And x1 dot t is ax1, x2 dot t is ax2. And that means again a will be x1, this one will be x1, a x1 x2. Okay, and therefore it is a phi t. So this shows that phi t is a solution of the system x dot equal to x. Okay, so thus it satisfies the first condition. And for the second one, it is obvious that since we have already specified that the column vectors x1, x2 at the point t0 are linearly independent. This means linearly independent. So then we can say that their determinant must be non-zero. This must be not equal to 0. That is, determinant of this is phi t0. So this is not equal to phi, not equal to 0, sorry. Yeah, 0. So this satisfies the second condition also. Now we have to check the converse statement. So conversely, suppose that let the condition holds. Condition holds. Conditions hold here. So there are two conditions. So the conditions holds. And let us suppose that phi will be written as two column vector x1t, x2t. Okay. So phi t is x1t, x2t. We need to show that phi t will satisfy the conditions of a fundamental matrix. That means these two column vectors will satisfy the system x dot equal to x, and at point t0, x1 t0 and x2 t0 will be linearly independent. Now from the second condition, it is obvious that since phi at t0, its determinant is not equal to 0, so you can conclude that x1 t naught, x2 t naught are linearly independent. So it remains to show that these two column vectors are solutions of the system. Now, from the hypothesis 1, that is phi is a solution of the system x dot equal to x. So from that condition, now note that phi dot t equal to a phi t, since phi t satisfies the system x dot equal to ax, and for that reason you will have, so phi dot t is x1 dot t, x2 dot t matrix equal to a x1t, x2t. So now we have, so x1 dot t equal to ax1t and x2 dot t equal to a x2t, and this implies x1t, x2t are solutions of the system x dot equal to x, and this proves that the 2 cross 2 matrix phi is a fundamental matrix. Fundamental matrix at, yes, at the point t0. So therefore, so now we have to exhibit an example for a system x dot equal to x. That is, we just write down a problem that verify the theorem, the above theorem, for the system x dot equal to ax, or the matrix A is 0, 1, minus 1, minus 2. Now one can easily check that the solutions for this system will be x1t will be 1 minus 1 e to the power minus t, and x2t will be t1 minus t e to the power minus t. So at any point t, these two vectors are, column vectors are linearly independent. You can check it on your own. You can check this easily, that these are linearly independent for any t. So x1t, x2t are linearly independent. at any t. Now so using these two column vectors, we are defining the matrix, that is e to the power minus t, e to the minus e to the power minus t, t to the power minus t, 1 minus t, e to the power minus t. So then a of phi t. What is a of phi t? If you calculate this matrix multiplication, then you will see that this product will be minus e to the power minus t, 1 minus t e to the power minus t, e to the power minus t, and minus 2 plus t e to the power minus t. Yeah. Now if we do the derivative for the function, for the matrix phi t, then you will see that phi dot t will be this matrix. So phi dot t will be a phi t. So that is phi satisfies the system x dot equal to x, that is phi t is a solution of the system. And determinant of phi t, it is e to the power minus 2t. If we calculate the determinant of this matrix, you will see that determinant of this is e to the power minus 2t. And since it is the exponential function, so the functional value will never be 0, it is greater than 0 for all t belongs to any r. So this proves that the verification of confirming that phi is a fundamental matrix is true, and this is true for any t, not only a particular one, it is true for any t. Now we need to put a deeper view on these facts. Observe that if we consider the initial value problem, just writing down x dot small x dot equal to small x, where at 0 the value is x naught, where a and x naught are constants, that is real numbers. Suppose that we are considering an initial value problem, x dot equal to small x, x at 0 the value is x naught. Yeah, and the solution of 1 is given by x equal to e to the power at x naught. You can easily check that this is a solution. And keeping in mind, one can expect that, so keeping in mind this solution, one can expect that the solution of the IVP, initial value problem, of the system x dot equal to ax, capital X dot equal to capital X, such that capital X at 0 equal to capital X naught, will also be of the form capital X is e to the power capital AT capital X naught. That means if we have the system x dot equal to ax with the initial condition that capital X at 0 is capital X naught, then one may expect that that the solution of this system will be of the form capital X equal to e to the power capital AT x naught, where e to the power capital AT is the expression capital I capital A. So capital X equal to e to the power AT capital X naught, where e to the power AT is the expression capital I plus capital AT plus capital S square T square by 2 factorial plus A cube T cube by 3 factorial and so on, and which looks like the expression of the function e to the power small x, exponential function at x, in terms of the infinite series, that is 1 plus x plus x square by 2 factorial plus x cube by 3 factorial and so on. So using this definition of e to the power exponential expression of this matrix, so we will have a theorem that which says that this solution is unique. That is the solution of the initial value problem x dot equal to capital X, where the initial condition is capital X at 0, its value is capital X naught. Then its solution is given by this expression, and this expression is unique. So let us have a look on the proof. So the statement is the solution of the initial value problem x dot equal to capital X with the initial condition that x naught is given by capital X is e to the power AT x naught, and this is unique. So this is interesting, that this solution actually looks like the solution for the system this, and e to the power AT has been defined to be the expression which resembles with the expression of e to the power AT, that is 1 plus AT plus a square T square by 2 factorial plus a cube T cube by 3 factorial and so on. Okay, so let us have a look on this proof. Now differentiating both sides of e to the power AT, the expression e to the power AT, we get, so d dt of e to the power AT, so it will be d dt of the expression I plus AT and so on, a square T square by 2 factorial and so on. So that means it is d dt of the matrix I, d dt of the matrix AT and so on. Now, since the term by term differentiation is possible, that is why we have put this differentiation into the bracket, because the series for e to the power at is convergent for all t under the operator norm. The series for this one, this, so this is convergent for all t. With respect to the norm can be defined as norm A is sup of x transpose ax by norm x square for all x not equal to 0, and norm x is x transpose x. So with respect to this norm, this series is convergent. And since this series converges, so we can put it inside the bracket, and then we can put it to each term of the series. So therefore we have, so the first one will be 0 0 0 matrix, and for the second one it will be A, and for the third one, that is ddt of a square t square by 2 factorial, it will give a square t, and after that it will be a cube t square by 2 factorial, and so on. Now taking common a, so we will have a into I plus at plus a square t square by 2 factorial, and so on. So that means it is a e to the power at. And this shows that, this implies that e to the power at is a solution of the system x dot equal to x. Now at t equal to 0, then what will happen? Then determinant of e to the power at equals to 1, and so it satisfies, this satisfies the property of a fundamental matrix for the system x dot equal to x with the initial condition capital X at 0 equal to x naught. So e to the power at is a fundamental matrix. Is a fundamental matrix for the system x dot equal to x with x at 0 equal to x naught. Now since x at 0 equal to x naught, this is the initial condition, so we must get that x equal to e to the power at x naught is a solution of the IVP. As because ddt of x equal to ddt of e to the power at x naught, and that means it is capital A e to the power at x naught, that is a x, and capital X as 0, it will be, so e to the power at x naught at the point t equal to 0. So at t equal to 0 we will have, so just put 0 in the expression of e to the power at. What we shall get? We shall get, it is the identity matrix. So it is I x naught, that is x naught. And this proves that x equal to e to the power at x naught is a solution of the IVP x dot equal to Ax with respect to the initial condition x at 0, its value will be capital X naught. Now the last checking will be to show that this solution is unique. This solution is unique. And for this, let us assume that, so for uniqueness, let us assume that capital X and capital Y are two solutions of the system. With the initial condition x at 0 and y at 0 both are x naught. This is the initial condition for both these solutions. And let x star t. What is x star t? That is xt minus yt. Just take the difference of two solutions. Then we see that x star at 0, it will be x0 minus y0, but x0 minus y0 will be the 0 matrix because x0 equal to y0 equal to x naught. So it is a 0 matrix. That is the 0 column vector. And ddt of x star, see, what is this? This is going to be ddt of xt minus yt. That is, so it is ddt of xt minus ddt of yt. Now ddt of xt is a x and ddt of yt is a y. That is a into x minus y, that is a x star. And this implies that x star is a solution of the system. So this implies that x star is a solution of the system x dot equal to x with the initial condition that x at 0 will be 0. And thus x star t will be e to the power a t x star 0. Now what is x star 0? Now x star 0 is 0. So that means x star t is equal to 0, and this is true for any t belongs to R. So this function is 0 at all points t. That means this is a 0 function. That is, this is a 0 matrix. And since it is 0, so x minus y equal to 0. So therefore x equal to 0. And from this proof, in the last part of this proof, the uniqueness part, we can observe that, so remark is that any solution of the system x dot equal to x, any solution of this system which vanishes at t0, such that x star t equal to 0 at t0. So any solution of this system which vanishes at t0 must be identically 0. So this implies x star t is 0 for all t belongs to R. Or in other words, one can say that the initial value problem x dot equal to x with respect to the initial condition that x at 0 is 0 has the unique solution x equal to 0. And from that one you can have this theorem, the uniqueness of the solution of the system x dot equal to x with the initial having the initial condition that capital X at 0 is x naught. Okay. Now let us list up some properties, beautiful properties of the matrix e to the power at. So properties of e to the power at, and we have seen that e to the power at is a fundamental matrix of the system x dot equal to x. Yeah. So the first one is, let us write down the expression of e to the power at again, I plus at plus a square t square by 2 factorial plus a cube t cube by 3 factorial and so on. Then the first one will be for a equal to the null matrix, then e to the power at is the identity matrix I. For a equal to identity matrix, e to the power at is e to the power t 0 0 e to the power t. Yeah. The third one is, it is obvious, these two are obvious. Yes. It can be achieved from the expression. This one is trivial because if we write down a equal to 0, then just put the matrix A equal to 0, 0 matrix here. So you'll see that each of these terms is 0. So therefore e to the power at will be the identity. And again, if A equal to t, then e to the power t will be, so A with the identity, so e to the power t will be, so from this one, that is so just writing down. Okay, let us have a look on this one. So e to the power it. Now what is e to the power it? It is I plus it I square t square by 2 factorial I cube t cube by 3 factorial and so on and so on. But each of this power of the identity matrix will be the identity matrix. So that means this is I plus it plus I t square 2 factorial plus I t cube 3 factorial and so on. Now taking common the matrix I, so then this expression will be I into 1 plus t plus t square by 2 factorial and so on. That is I e to the power t. So therefore it is e to the power t 0 0 e to the power t. Yeah. For the third one, third property is, let A be the diagonal matrix. Let lambda 0, 0 mu. Then e to the power at is e to the power lambda t 0, 0 e to the power mu t. Yeah. So this one can be achieved by, so A is lambda 0, 0 mu. Then what is A square? Lambda 0, 0 mu, lambda 0, 0 mu. What is it? So this is lambda square 0, 0 mu square. Similarly, if we do the cube, you will see that this will be lambda cube 0, 0 mu cube, and so on. So therefore, so a to the power at will be I plus at plus a square by 2 factorial, and so on. Okay. So this is 1001 plus, now A is lambda 0, 0 mu. So therefore this one is lambda t 0 mu t plus this one will be lambda square t square by 2 factorial 0, 0 mu square t square by 2 factorial, and you can do this for the other terms. So now just adding these matrices together, we will see that the first entry will be 1 plus lambda t plus lambda square t square by 2 factorial, and so on. And the second entry is 0, and the third entry is also 0, and the last entry is 1 plus mu t plus mu square t square by 2 factorial, and so on. So that means this is the e to the power lambda t 0, 0 e to the power mu t. Yeah. And the fourth property is, if A is the matrix of the form P inverse some dP. What is D? Now D be a diagonal matrix lambda 0, 0 mu. If this happens, then this implies e to the power at is P inverse e to the power lambda t 0, 0 e to the power mu t p. And this is very easy to check, because since A is P inverse dP, so A square will be, so it is P inverse dP dot P inverse dP. So that means, just using associativity, we will have it is P inverse d square P. Similarly, if we do the A cube, then it will be P inverse d cube P. A to the power 4, it will be P inverse d to the power 4 P, and so on. So e to the power capital AT will be P inverse e to the power dt P, that is P inverse e to the power lambda t 0, 0 e to the power mu t P. So this is obvious. Now number 5 is also trivial. I shall leave it to you to check. That is, if for any two matrices A and B, if AB equal to BA, then e to the power A plus B t, it will be e to the power AT dot e to the power BT. So this has been left as an exercise to you. Now the sixth one is, this is exercise. Sixth one is, if A is a nilpotent matrix. What do you mean by a nilpotent matrix? A square matrix A is said to be a nilpotent matrix if for some k, a to the power k will be a nilpotent matrix of nilpotency k or k naught. What do you mean by nilpotency of a nilpotent matrix? Now, since for a nilpotent matrix you will find an integer k, a non-zero integer k for which a to the power k is the zero matrix. So taking all those k for which a to the power k is 0, then you will see that this set is non-empty set of, this set is a non-empty set of subset of the set of naturals, and for that reason, by Euler principle, this set must contain a least element. That is, there exists a least positive integer k naught for which a to the power k naught is 0. This k naught will be defined to be the nilpotency of the nilpotent matrix A. That is, you can write down it as a to the power k naught equal to 0 a to the power k naught not equal to 0, but okay, a to the power k naught plus 1 equal to 0. Yeah. Then e to the power at will be I plus at plus a square t square by 2 factorial and so on, plus a to the power k t to the power k by k factorial plus a to the power k naught plus, this is k naught, sorry, plus 1 t to the power k naught plus 1 by k naught plus 1 factorial, this is also k naught, and so on. Now since a to the power k naught plus 1 is 0, and you will see that actually a to the power k naught plus p equal to 0 for all p greater or equal to 1. So after this term, each of the term is 0. That means the expression remains I plus at plus dot 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 a to the power k naught t to the power k by k naught factorial. Yeah. So this is the sixth property. And the last one is the seventh property, such that if A will be of the form PQ minus QP, that means if A can be written as PI plus QJ, where I is 1001 and J is 001 minus 10. Then e to the power at will be then e to the power at will be e to the power pi plus qj t, that is e to the power pit dot e to the power qjt. Yeah, that is e to the power pit into I plus qjt plus q square j square t square by 2 factorial and so on. Now since j square equal to minus I, j cube equal to minus j, again j to the power 4 equal to capital I and so on. So e to the power at will be e to the power pit into so it is 1 I plus qjt. Now what is j square? J square is minus I, that is minus q square t square by 2 factorial capital I, plus the next one is q cube j cube t cube by 3 factorial. Now j cube is minus j, so that means this one is minus, so it is minus so j cube is minus j, so it will be minus q cube t cube 3 factorial, and here it is j, and so on. So this portion can be rewritten as e to the power pit, now 1 minus q square t square by 2 factorial plus so on, plus qt minus q cube t cube by 3 factorial plus so on into j. So that means it is e to the power pit. Now this expression is for cos function of qt. This is I, sorry. So cos qti plus sin qtj. Yeah. So this proves the
এই ব্যাপারটা কোথায় গেল? এই cos qt
কোনটা বললো?
এই cos qti এর এই ব্যাপারটা
দাঁড়াও বলছি, এইটা তো cos qt। হ্যাঁ, তা cos qt মানে কি? cos qt সেই যে আমরা সিরিজটা করেছিলাম না, cos qt মানে 1 মাইনাস, যেমন আছে সিরিজ করেছিলাম, cos x মানে কি 1 মাইনাস x স্কোয়ার বাই 2 ফ্যাক্টোরিয়াল ডট, sin x মানে কি x প্লাস x কিউব বাই ফ্যাক্টোরিয়াল, মনে আছে?
এটার সাথে এটা
হ্যাঁ হ্যাঁ, এগুলো তো সব রিয়েল এগুলো। ওকে, সো ইট ইজ cos qt প্লাস cos qt, এখানে should put I, এই যে this I, so cos qti sin qtj, yeah, this one, this j plays the role of the imaginary unit because I square is minus 1 and here j square is minus 1, right? Actually it is minus I, but okay, it looks like that j is minus I, that means j square is minus 1. If we can establish a correspondence between the complex number field and the set of all those matrices of the form PQ minus QP. Okay, we can always set up a map that is P plus IQ. It will go to PQ minus QP. Then we can show that this map has some interesting properties. This is a map from the complex number field to a subset of two matrices. Okay, and we can always check that this complex field is actually isomorphic to this one. Okay, so these are the 7 properties of the matrix, fundamental matrix e to the power at of the system x dot equal to 80. Okay, so let us stop here.